How's it going, everyone? Welcome to the next video. Today we're looking at indices as logarithms. So to start off with, a logarithm is also another name for an index. And essentially what it means is if we've got a value n, when my pen works, n over here, we've got the statement n is the same as, or n equals a to the x, is equivalent to x equals log a of n. So what it's meaning is if we have the situation, for example, 2 to the x equals 5, and we're trying to find out what x is. So 2 to the power of what gives us 5? Well, to be able to work that out, we have this relationship here. So we've got n, in this case it's 5, a is going to be 2, x is x. So I can actually solve as x is actually the log of a, which in this case is 2, and n, which is 5. So my solution would be log 2 of 5, and that would be how I would work it out. So this is irrational. The power of 2 gives the number 5 is not rational. A decimal approximation for logarithm can be obtained using calculator. Okay, so I can work what that actual answer is. Not all expressions containing logarithms are irrational, sorry. So solving the equation 2 to the x equals 8, x would therefore be log 2 of 8. So what it's saying is, and we've had a look at this last chapter, 2 to the x equals 8, so we're saying 2 to the what gives me 8. Well, 2 to the 3 would be 8, so x would therefore be 3. Whereas we can do the situation here, x equals, so instead of working out that this way, we would say x is log 2 of 8, and if we do that on our calculator, it would be 2. So basically when we see this, we're almost saying 2 to the power of what gives me 8. So the base to the power of what gives me 8. So that's what we're looking at. Before I go on, just a couple of little notes. On your calculator and other operators, you can see different types of logarithms. So most common, especially for physics and chemistry, is what's called log base 10. So you can see that it's either written like that, sometimes it's written as just the log. Okay, meaning log base 10, it's the most common, use it on scientific calculators and so forth. Another operator, and what we'll be using in methods, is what's called the log base E. So log base E logarithms are called natural or Naperian logarithms, basically named after the inventor John Napier. A bit of history for you there. So these logarithms occur extensively in calculus when we get onto that chapter. E, this number E itself, is actually called Euler's number. So Euler, obviously a mathematician. And like pi, it is a transcendental irrational number that has great importance in higher mathematical studies. And basically you'll see that quite a lot. On your calculator, you find that log E as ln. So if you see ln, it means the natural log, or log base E. Another common log is log base 2. And you see this probably not as common as either of these two. This is more in terms of what we call number theory or um, when you're looking at encryption and so forth. So we probably won't be using much of those. So these two, the main ones, so log base 10, log base e, again you'll see this more in the science areas, this is more in the math cas calculus era. Going on to logarithm laws, so we've got table here, we've got 5 log laws. Make sure you copy these down, these are very important and you'll be using these quite a lot. I'm not going to go through the proofs of how you get these. You can have a look at that yourself. That's on page 581. So just note that we've got these log laws here. And we'll be using these in a couple of examples shortly. Logarithms as operators. So just for the situation, we say if we've got the number m equals n, then we can say that the log a of m is going to be the same as log a of n, and vice versa. So if we take the log, basically we've got m equals n, we're taking the log of a of both sides, so they're equivalent. So it's an important tool when solving identical equations. So again, let's have a look at 2 to the x equals 5. And we had the solution that x equals log 2 of 5. Another way of working this out. So we're going to say using this method here. So we've got 2 to the x equals 5. We're actually going to take the log base 10 of 2 to the x and log base 10 of 5. So basically taking the log base 10 of both sides, using log 5 logarithm law number 5. Okay, so we've got something to the power of p, 2 to the power of x. Okay, so that's going to be p log a of m. So what we say is basically this power here comes down the front. So it'll be x times log base 2 equals log 10 of 5. And now I've got something, so x times log 10 of 2. So x is going to be log 10 of 5 divided by log 10 of 2. Okay, so same answer, different way of working it out. One more little note, so change of base for calculator use. So we've got the equation a to the x equals p. So again, x is going to be log a of p, and can be solved in a similar way we did to 2 to the x equals 5. So we actually get the solution using this method here. We get x equals log base 10 of p divided by log base 10 of a. And this enables decimal approximations to logarithms to be calculated on scientific calculators. So we're just making it easier for ourselves, is essentially what we're doing. We'll go on to some examples. So example 5. So expressing 3 to the power 4 equals 81 as a logarithm. So 3 to the 4 equals 81. Okay, so the index form is given by base 3, and index or logarithm of 4, and number 81. So using from our first page, n equals 81, n equals a to the x, sorry. Um, so we can say x is going to be the log of a of n. Okay, so I can say n in this case is going to be 81, a is going to be 3, x is going to be 4. So I actually say that 4 is going to be the log in a, which is 3, of 81. Part B, so express log 7 1 over 49 equals minus 2 as an index statement. So this is going backwards. We've got a, in this case, is 7. N is going to be 1 over 49. And x is going to be minus 2. So our log statement, or index statement, sorry, is going to be 1 over 49 equals 7 to the power of minus 2. Okay, or I could say that means the same thing. Part C, so solve the equation expressing the exponent x to two significant figures. So again, I've got x equals log, and a is going to be 10, n is going to be 12.8. Using our calculator, we'll get 1.1. Then part D, solve the equation log 5 of x equals 2. So I can say so basically we've got this, need to convert it into something like that. So I've got n, which is actually x, a, which is 5, and my x is actually 2. So it's going to be 5 squared, which we can actually say is 25. So it's just using this information here. Example 6, simplify the following using the log rules. So we've got log base 10 of 5 plus log 10 of 2. If we go back to our log laws, we've got log of something plus log of something, so we're using number 3. So it's going to be log of the same, just note that these all have to be the same base. So log of something minus log of something, they have to be the same base. So we've got log 10 of something plus log 10 of something equals log 10 of the m times n. M, which is going to be 5 times n, which is 2. So we actually get log 10 of 10. And if we go back to log law, so I'll just cut these out. No, I won't. Sorry. So if we use Law 2, sorry. Log 10 of 10 is going to be 1. So we've got log 10, 10, so it's actually 1. Part B, so got the same base, log base 2. We're taking it away, so we actually get, using log law 4, we get 80 divided by 5. And if you work that out, we get log base 2, and that should be mental blank, sorry, 16. So 80 divided by 5, 16. Right. Now I can actually extend this and say that 16 is actually 2 to the 4. And then using law number 5, I can bring this power out the front. And because I've got log base 2 of 2, it's actually 4 times 1, which is just 4. Okay, so that's it. That's part B. Part C, and we're getting more complicated. I'll cut this out. Just so we have more space. So we got log 3, 20, 2a to the 4 plus 2 log 3 square root of a on 3. Okay, quite complicated, um, but we've got the same base on both. Now I can't use my law to adding yet because I've got this 2 in here. So I just need to use law number 5 first, to bring that into the log equation. And if I do that, I'm basically squaring everything inside there. Square root times and squared, they cancel out each other. And once I've done that, I can use my third law, log 3, and they're adding, so I go log 3, and it'll be 2a to the 4 times a over 3. And just simplifying a little bit, we get 2a to the 5 over 3. Oops, sorry, that should be a 2, which means they cancel out each other. Sorry, I'll just fix that up. And then final step, using our last law, bring the 5 out the front again. 5 log a, log 3 of a. And that's all we can do for that one. And the last one, so we got log a of a quarter divided by log a of 2. And I can actually rewrite that quarter as 2 to the minus 2. Which means I can bring that power out the front. And because I've got log A of 2, log A of 2, and I can cancel those out, so I just get minus 2. Okay, so really, log laws, it's really about manipulation, using the 5 laws that we've got so that we get a simpler answer. So it's just going to come with practice. Might be fairly confusing to start with, but with practice we'll get through it, so just make sure you ask questions. We've got worked example 7 left. So state the exact solution for 5 to the x equals 8. Calculate the value to 3 decimal places. So I've got 5 to the x equals 8. So I say x is going to be log base 5, 8. So that's my exact solution. If I put it in our calculator, if we only had our scientific calculator, I would need to change this base. So we're just going to have a practice of doing that. On your Casio, you'll be able to do that anyway because there's a function where you can input that different base. But using our scientific, we can only have the natural log and base 10. So I'm just going to go through an example of how to do that. So if you remember, log A of P is the same as log 10 of P divided by log 10 of A. So in this case, we've got log base 5, 8. So that's going to be the same as log base 10 of 5. 8. Okay, because P is going to be number inside the logarithm. And that's going to be divided by log base 10 of 5. So we would be able to work that out in the calculator or scientific. And if we do that, we get an answer of 1.292, which is an estimate. Because we're rounding off, there'd be rounding errors with the decimals. And part B, calculate the exact value and the value to 3 decimal places of the solution. So we've got 2 to the 1 take x equals 6 to the x. And I'm going to take the log base 10 of both sides. So I get log 10, 2 to the 1 take x equals log base 10, 6 to the x. Using our log laws, we get 1 take x out the front. Log base 10, 2. Bring the x out the front again. So I got 1 take x times 10, well, log base 10 of 2. So when we expand it, we actually get 1 times log 10, 2. Take x log 10 of 2. And that's equal to x log 10 of 6. And if I bring the x this term across. So add, because I've got an x in both terms, I can take x as a factor, and I would be left with that. Now I've got log base 10 of 6 plus log base 10 of 2. I've got the same base, so I can actually use our third law, which would be 6 times 2. And if I work that out, I'll put it up here. We get x log base 10 of 12 equals log 10 of 2. And final thing, just divide which will give, you can put that in your calculator and get a decimal estimate, or you can keep that as the exact value. So an estimate would be 0.279. Okay, so that's all we need to do for that one. Now I've got one more. I'm just going to quickly grab that. I forgot to put that on that. So I worked example 8. Last one. So solve the equation log base 6 of x plus log base 6 x take 1 equals 1. So just rewriting this. Now because I've got log base 6 for both, I can go log base 6 equals x times x take 1. If I do that, and I'll expand those brackets. So x times x gives me x squared. Take x equals 1. Now converting from logarithm form to index form. So if I basically we've got log base 6. So if I put it to the base of 6 of both sides, they cancel out, is essentially what we're doing. Now I've got a quadratic. So take 6. Just need to solve using our null factor law. So I'll have x take 3, x plus 2 equals 0. So x equals 3 or minus 2. Now, that's our solutions, but we need to check the validity of both the solutions in the original equation. Because of this minus, or because of the possibility that it doesn't exist, one of those don't. So if we go back and put them in, so log of x, and we'll say 3 to start with. So just check that that equals 1. So log base 6, 3 plus 3 take 1. So on the left hand side, log base 6 of 3 plus log base 6 of 2 would be this, and then 3 times 2 gives me 6. Log base 6 of 6 is 1. So that and that are equivalent. Yes, so that is a solution. So x equals 3 is true. Now just checking the other solution. So minus 2, minus 2 take 1. So checking that it equals 1. Log base 6 of minus 2. Um, because I've got a negative, basically means doesn't exist. So we can say so we reject the solution x equals minus 2. Okay, essentially what we're saying is 6 to the power of what gives us minus 2 for this little bit here. 6 to the power of, well, it doesn't exist. 6 can't get 6 to the power of something to equal a negative. So that means that doesn't exist. So we reject that. Okay, so our solution is x equals 3. So that's 11.3. It will take some working out, some practice to get through some of these. A lot of it's just about manipulation. So have a go at the questions. Please ask for help. Please ask questions for help. Thanks for watching.